seriously kidding me right now? Shit. Goddamn fucking kick. Trying to get in on that website. The freaking login webpage goes dysfunctional after 1 minute. Then you gotta go to a website email to get the login. Then that disappears after 1 minute if you don't get it in time. Yeah, I'm wondering if I can get anything done. What did I just do? Okay, that didn't work out very well, did it? So, I was going to put down discrete circuits, and then I'm thinking to myself, then I was thinking, like, I have a circuit that I need to build, and I have sort of like, what do I have? I have a prerequisite, a sort of a prerequisite to have everything as much as possible, to have everything the same or symmetrical. So like if I use a certain type of setup for a circuit and I'm going to have two parts to that circuit, I want the parts to that circuit to be the same or use the same materials as much as possible. Now, let's see, we are logged in. We're streaming. Gotta make sure that this is turned on. I don't know why this is like this. Why is this stupid ass shit on here? Okay, that's paused. This one. Oh, maybe. I don't know what's going on over there. So there's a transistor. Like I was thinking, well, I can build a transistor circuit, and the first project I need to do is build like a circuit that inverts the phase of the input. And if I use a transistor type circuit, I've got to have another transistor circuit to input the same signal that does not invert the circuit. I can't have two circuits to re-invert it again, because I don't know, I'm just thinking it would create an issue. So I tried to build this op-amp setup. Now, this particular stage of, well, actually, you know, I could probably bring up. What did I do with my pictures? Documents. Let's see. Face sounds like the music from that space game I used to play. What the heck was the name of that? Anyway, so if we look at this circuit, this is supposed to be, you've got one, there's only one signal source, and then this comes back up around and feeds this. They've got a unity gain op amp. I don't know if you can see this in the stream or not. There's a unity gain op amp in there. See, my problem is if I do this, see, that's just minus, and you're supposed to get a phase reversal. And I had a bunch of trouble trying to get the equipment to show it. Circuit over here. Let's see. Actually, what I can do is I'll grab a circuit and just kind of explain it a little. Let's see, I'll copy this one. And now just put it. That kind of goes on there. You know what that music's going to be? Conducive to my atmosphere. Why can't I make this bigger? Anyway, I was going to use transistors. I was going to use a transistor circuit because, so my other stream, I put down discrete circuits, okay? Discrete circuits is the least number of components to build a circuit to get the desired output. So if you use an operational amplifier, which is this triangle thing, I wonder if I can get the fuck out of there. Fuck you. Damn fly flying around my house. I wonder if I can just grab this. Well, that doesn't work very well. And so I thought in place of the op amp, I was going to use a transistor circuit. So, okay, so what I wanted to do is, let's see here. Let me go ahead and make a box. I'll just color it red. We'll use this. We'll use maybe this. We're going to get rid of this section here. And I'm going to fill this in with white. I guess we're not going to fill it in with white. Huh. Well, let's do it another way here if it wants to be stinky like that. I'll just do this. I'll leave that box in there. So the reason I'm doing this is because I want to explain something, but I wanted to get, like, I don't want it to be confusing. I'm not exactly sure what that other circuit was over there. there was an output op amp, and then it fed back to this one on the bottom here, which sends a signal. This converts it to whatever it does. It looks like it pulls down this transistor, does something with this input. And you've got a phase shifted output. Oh wait, well, that's the original signal. It just goes in, it gets is a unity gain. I'm not sure why the capacitor's there. This is phase shifted, and the other one, it's negative. It goes back into another amplifier, which changes the phase back to the original. So what you've got is you've got two amplifiers doing one job and one amplifier doing one job. And I'm wondering, I think if you use an NPN transistor, you know, I could probably design the circuit that I'm thinking of. It's in my head, and I could actually look it up. That would be, I think it's a Class A amplifier. So what we could do here is we'll set up a web page. We could do this, go to images, and I'm looking for a particular type of amplifier. That's a 2N222. There's one there too. This is a good example here. So let me bring this up here. Where's my? We gotta add a web page. Add. Right. Window capture. This stuff is not websites. Web page. And this one here, we'll just go ahead and drop this down to maximize the size of the picture. Put this back down here. So this circuit on the right here, 2N, okay, so if we go to another web page, 2N, there's this one, whoops, that should have another 2 in there, and then we're going to look up another one, 2N 3904, and I don't remember which is which here, 2N 3906. These are like really old small transistors. This is a PNP. Now if I could use one circuit for each thing that I want to do, use the same type of components, use the same or close to equivalent type of transistor in each circuit, I think that's the optimal way to do what I'm doing. And the other thing that I need to do is I need to open up another, or could I just actually let me go back. What am I thinking? Yeah, let me put paint back up here. What I'm gonna do is I don't want to save it, so we're gonna change this, and then I'm going to show you what my idea is of what exactly it is that I'm doing. So let's say at the beginning we have let's see, let's say we have an antenna which actually looks like a triangle. It doesn't look like this, but we just make that and then make a line like so. Looks like a flag, huh? This is an antenna, and also let's put down an orange box here. Like, oops, that's not an orange box. And I can't change things. Once I draw stuff in here, I can't change it because I don't know what the hell is going on. Let's put a box here. And then we're going to put in, oh, I don't think that works. Let's just do it freehand. Let's make another greenish looking thing inside this box. And then we're going to use a blue line. So this is going to be a block diagram, and let's use this one. So we want, this is a signal generator, this thing in the box here, and then we're going to have, actually that's not really the way to do that, but I'm going to do it anyway. And then we'll have another line coming out of here. It's the same signal, and then the green one, again, this is gonna go over here somewhere. And then we're gonna have another box. Actually, let's draw this figure here. And then we use that color. I should just use a regular line. That's a little crooked. You get the idea. So the generator with the two blue lines represents a calibrated signal source, and it is going into both the circuits. Oh wait, let me think. The input. Okay, something's. Let me think here for a minute because something's not right. Oh, you know what? This has to be at the beginning. Or does it? I wanted to build a preamp circuit. Let's see. Let me see here. A preamp circuit. I think I can do this. So let me think. Let's use the dark. Actually, let's maybe use this color. Alright, so I'm just gonna make a box. I think this is what I'm gonna do. This is a box here, and this is a box here, and they're the same color because they represent the same circuit. And these are preamp circuits. Preamp circuit. Maybe with a filter. You don't usually do. What you usually do is you amplify and then filter. You put a weighted filter on here. Am I doing this right? Where's my... I am. I still got my line. Let me see here. Oops. Oh, come on, get out here. I have a text field. Okay, so preamp filter. Now, these two circuits don't care about the phase relationship, because so this would be input signal plus noise. This is, wait, this is an antenna. What did I do? This isn't correct, this green line. But I think no, that's not correct. Wait a minute here. Alright, give me text. Give me this color. So this is going to be input signal with noise. Actually, let's put down input signal with its noise. And then what was I thinking of how to do this? Doesn't that go in? Oh, it does actually go into both. Okay. That's what I'm thinking. Let's see, copy, paste. Wait, that isn't correct. I know why I wasn't doing this right. So that goes there. Edit. It's not gonna work, is it? Yeah, it is. Copy, paste. I get the brown with a line. Okay, that makes sense. So that's one FET. Oh, I should gotta put that down here too. See this color. And these are going to be high gain, low noise, FET 2 and 19s. Now we've got, and this is, I could put down, let's see here. This would be, what color would this be? This color here. Calibration, signal, 1K, etc. Okay. So now we've got to do a phase reversal. I think. I don't know if we put another amp and another filter on here. So I think at this point the signal is going to be loud enough, because what we got to do is we got to start, let me do something else, because I'm not sure about there should be let's say filter FILT filter here or after. Put this, edit, copy. Did I do something wrong? Can I just move this? And then we'll grab the bucket, black, and fill that in. Now let's see, let's do another box, same color, and we could just put in box here. It's a little bit smaller, it represents sort of like one item. So that's a question mark. These are whatever that is. So then we've got a signal coming out, and then what we're going to do is let's put a line here. If we can use that one. Now we've got a signal coming in, and they're both essentially the same circuit, but they're amplified. And there's two of them. Okay, that makes sense. I didn't even think about doing this. It's funny, it's like when you work on a project and then you start throwing the design out, you think to yourself, wait a minute, something doesn't look right. And then you think, well, you know, you can do something different. So we're going to just put an arrow here. Oops, daisy. That denotes that this color, it's the same signal. So now we're going to have another box. Well, let's use a darker blue. And this is going to be, this is what I'm building. Oopsie daisy, I didn't want that there. This is what I'm building tonight. I need a box. There's a blue box there. Doesn't look really the same. Okay, and let's see, we're gonna have minus and positive. Let's see. So yeah, let's do this dark green one. This is gonna be actually, you know what? Let me move this arrow up here. You know, I'm using a transistor circuit. using the op amp for this. So that doesn't have to be there, does it? It can be in the middle. I don't know how to undo this stuff in Paint. So this actually can be in the middle. Alright, so let's go to here, and we'll put down the description. So this is a well, that didn't really help very well, did it? Small signal transistor amplifier. See, I don't know about that filter yet. I mean, I just don't know. Let's see. We got one. Might be an NPN. Let's see here. 2 and or actually, you know, I think it might be the 3904. I think it's a 3904, but I gotta look. Or let's put down or 2 and 3904, and 2 is a 2 and 3906. And then we put this here again. It probably should be a different color because, well, that's okay. Let's just do this here. This is 1, and this one is 2. And put another thing here. Phase 180 degree out on one amp. Now we're going to save this as let's call it trans amp 1, meaning transducer. Now I'm going to go back to the web page here, if I can find my thing. What time is it? Let's see here. We're going to show the web page. Video capture. Let's go to the 2N222. It's one of the most common transistor amplifiers. I've got a few of them. It's an NPN. Why is that garbage there? They've got canned versions. Oh, they cut this in half to show you. Look, they even plastered that stuff on the bottom too. It's a high voltage collector emitter, which kind of bothers me a little bit because 500 milliwatt, I mean, this is cranking. It goes up to 300 megahertz. Maybe that's okay because what we want to have we want to have circuits that have high transient response, and I'll talk about that in a minute. But what I want to look for is the other one, 2 and 38 19 spec. Okay, let's see, that's its components. There's an PDF for Mauser. So the preamp circuit consists of an FET. It's extremely sensitive. I mean, this is what I use for everything in my. I use this to collect the static charges, pretty much everything. So an FET, when it's in a circuit, let's see if we can find. There's no circuit. 0 to 25 degrees centigrade, which is room temperature, power dissipation in milliwatts. If the temperature goes up, power dissipation goes down, so I'm not worried about that. Gate source voltage. Gate. What is this? Is source. Drain, gate, and source. So one is the drain. It doesn't show the schematic on here. That's a little bit disheartening. I don't want to look at this one. A lot of schematics have applications. Wide storage, temperature range, forward gate current, 10 milliamps. Equivalent input noise voltage is like 6 nanovolts per square root of hertz, like it's really small. On resistance and output conductance versus gate source cutoff voltage. Use these to design your circuit. Drain source on resistance. This is in ohms. So this looks like it's a, when this thing is turned on, the resistance is low. It's in the 100 ohms. That doesn't make any sense though. I don't understand half the stuff. I can't remember a lot of it. Now this graph is this is your gain graph. When you have higher drain current, you have and you have a higher drain source voltage. This gives you your amplification, I think. I forget. Anyway, I just go for the circuits. Let's see here. Low signal amplifier circuit images. No, that's not the correct diagram for the 3819, because that looks like an NPN transistor and it's not. It has a little gate thing at the beginning here. I don't know what kind of a circuit this is. It has two things going in here. It's got two input sources into one transistor. I'm curious as to what this is. So that tells you what's where. You look at the flat face and it tells you source, gate, drain, that kind of thing. Look at these stupid ass advertisements over here. The hell? That's just a DC. This is using this for a timer. An audio mixer. technically you wouldn't really want to set up an audio mixer like this because you don't, this is not, I don't even want to look at this. Let's just forget that. What we're looking for is something like this one. Okay, what does this say here? Why is my signal stronger in the positive than in the negative when I use such and such? I've created a JFET amp for a small signal. I run tests on so you get this weird where my signal is stronger in the positive, like 40 millivolts. Standalone JFETs are not linear over much range. Today's audio grade op amps have THD as low as, geez, that's pretty low. Some 145 dB, whatever the heck that is. So that's an interesting point. It says that it's not linear. So when we set the circuit up and set the calibration signal, we do a sweep to determine what the linearity is of the circuit. And if some signals get amplified at a higher rate, that's why we put in the filters. But I don't know, maybe it's important after that preamp stage or not. That looks like a pretty good circuit. So you've got a 7 megohm and a 1 megohm input resistance. Now, typically, when you have these megohm resistors, they add an excruciating amount of noise to the circuit. And maybe that, because this is fed back on this plus line, it could be the amplification section and the gain section here. This is a circuit that somebody built, so let me just go through here and see if there's, what is this here? This looks interesting. There's a video here.
Hello guys, welcome back to my channel. In the previous video we discussed about the output characteristic curve and the transfer characteristic curve of this n-type JFET.
So now this one here, this circuit on the bottom, I would not do because it doesn't have temperature compensation. It doesn't have the feedback. It doesn't have the stable. Well, just see what he talks about.
3819, and we saw how to plot these VI curves. Okay, now in this video I would be going to design the self-biased common source amplifier based on the same FET that we have. So in order to start with this, we have to select a quiescent point on this IV curve that we.
There's one simple hearing hack.
Oh my god, I hate this stupid effing ad. I'm sorry about that, but there's nothing I can do about it.
Source FET amplifiers. We probably don't need a cap because the gate is virtually at ground, but I don't necessarily know what's going on with this circuit, so at least at low frequencies, that's infinity. You know, it's not really infinity, it's a really, really big value, but at least at low frequencies we can approximate it compared to other resistances in the circuit, we can approximate it as infinity. Okay? All right, now let's connect everything else up. So, off of the gate we have the gate resistor, the biasing resistor. And of course caps are going to short out for AC, so here's our input voltage. Off of the FET's source, this cap shorts out the RS2. We're only left with RS1. So I'm just going to call that RS, little rs, AC value of RS, to indicate swamping. And I'm going to draw these two guys separately. Of course, the power supply is an AC ground, cap shorts. RD goes to ground, as does RL. All right. Okay. So the first thing,
Oh. What? We talking about FTL?
and we can combine these two guys in parallel. You can call that little RL or little RD, your choice.
What I'm doing is I'm talking about the middle parts of the circuits. Faster than the FTL stuff comes in when I get the amplification circuits and the filtering circuits built. Then we got to talk about the type of input circuits and how to access those input frequencies, and creating what I do is I create an infinite field. I kind of talked about this in the other stream. There's an infinite field localization area, a specific area in space and time, and I try to pick off a signal from that infinite space. I try to create something that creates like a wormhole into that space, and you do that by a few different methods of creating a fractal dimension. You can do it with electronics, with statics, magnetics, stuff like that. So I want to create this field, and then I want to stick a probe into this field and see if I can pick up signals that are not normally supposed to be there. And that FTL signal is actually coming from supposedly another dimension. That's where the FTL happens. There's no time. It's like a portal. If you've ever seen some of those movies where the guy jumps into the portal and he's in the next place like instantaneously. That's the transducer portion of my streams, which I haven't gotten into yet, but I'm just doing the circuit design to amplify the signals and reverse some polarities, that kind of thing, to pick up low signals in the noise.
Right. Looking at the impedances, if I was to look at the input impedance,
I thought I turned it up.
now what do we see over here for a ZN?
I don't know if you heard most of that or not.
That's going to be this RG in parallel with the Z end of the gate.
Yeah, we're talking
but as we said,
he's talking about these FETs.
GMRL divided by 1 plus GMRS.
I want to do something else. That's YouTube. Let's see. What is the best low FET amp? Quietest FET selection for an audio input stage. So fractals are pathological. That sort of geometry is ruled out in what sort of gravitational theory? Okay, so you're mixing and matching a couple of different things here. Although gravity is probably a part of what's happening, it's not like in Einstein was trying to come up with a theory of relativity, a special theory of relativity that includes all things. Well, gravitational waves could be part of that, but I think they're insignificant in the area that I'm dealing with, which is not, there's no gravity involved. What's involved is a feedback loop, and the feedback loop is what creates an infinite space, and we can set up the feedback loop such that it becomes a fractal, and we can manipulate the numbers on that fractal to create this stable type of feedback system. And they're called strange attractors. And so by creating that strange attractor within a certain field of electromagnetics, whether it's static or magnetic or whatever, I believe that that's where a wormhole can be created. I mean, I'm just throwing that out there because I know for a fact that the person that I visited, he did he used video feedback loops, and he was getting pictures. He was receiving pictures from these different places. So I think what was happening was when he set that camera just right, he was actually peering into a portal. A portal exists in that time and space, and he was able to find that portal and see what was on the other side. Wormholes are gravitational phenomena. Uh, well, it could be one type of phenomena, and I'm just saying that what I'm doing is not related to gravity, so I just throw that out of the equation. Um, I couldn't tell you. I just couldn't tell you. All I know is what I know about feedback circuits, how to create a type of space in time to allow some strange things to happen, and how to be able to build a transducer that kind of goes into that field, and then see if we can pick up some strange shit. I don't know, but it's fun trying. It's fun messing with it, and that's going to be the more challenging part of the stream, is to try to figure out how to set that up. I did it once. I tried it once with using a flame, because a flame is a really good random source, and I tried to mix two different polarities of energy coming out of the flame, but I picked up a signal. It was like coming out of this op amp, and it sounded like a religious radio station. It was like clear as day. There's no antenna connected to it. This was coming right up out of the flame, and there was no antenna, and that's the problem, is that when you create these circuits, you could be creating a resonant frequency that's tuned to some radio station, and so that's why I'm using either electromagnetic or electrostatic fields as uh, a mode of creating these feedback loops. I haven't even got into that yet, so it's crazy. But yeah. So I'm just looking up these FET amp circuits. Yeah, this is a good one here, because this talks about noise temperature, um, and it relates. You can relate noise temperature to input resistances and that sort of thing. And I talk too quick. Let's see. Defining the JFET noise temperature. Well, that's the noise temperature of these transistors and FETs is much lower than the signals that I'm going to be getting to amplify, hopefully. Um, and there's really no circuits in that one, but that just talks about noise. So what I was doing, okay, so there's two transistors. I believe it's a 3906, that's a PNP, and the 3904, I hope. Maybe that's the NPN. I think the 3904 is. Yeah, see, it doesn't. This is an NPN. I think it's these transistors I gotta use. So I gotta compare some specs on the 3904 and the 2222. And that's what I'm doing, because so this is an NPN. It's a low signal amplifier. Oh, is this like Kaluza Klein theory? Then we use 5D geometry to include electromagnetic interactions into the What do you mean by metric tensor? Because there are, well, uh, a tensor defines energy from a specific point, and whether or not the energy, I don't understand the energy in the field that I'm looking at. What I'm doing is I'm creating a field, and that field is a stable, um, it's a stable, strange attractor field, which is going to be quite difficult to set up. You have to use, like, probably I have to use, I'm thinking I've got to use micrometers to be able to adjust the wavelengths of the field, because I'm thinking of using ultrasonics. Supposedly, the information that I got was that um, the beings that exist in higher dimensions obviously are going to be in a higher dimension than an electromagnetic field, which is a really low dimension. That's like, we're talking hertz, um, versus ultrasonic, which is like way up into the terahertz or something, you know. And so I did calculate, I did do a stream, my last stream, I had a picture of how I'm able to adjust a mirror with a laser source, and I can use that as a chance to try to eliminate, or to try to create a positive and a negative field. And I want to cancel those fields so that I just get this signal. It's a little bit complicated because you don't see the whole picture, and that's talking about everything aside from this electronic circuits, which is what I'm trying to build. It's like a block. So that block is the input source, and what I'm doing is I understand you're trying to figure out how do I get my signal from a source that's supposedly just a wave. Well, it all starts with EVPs, electronic voice phenomena, ghosts in the box, that kind of thing. Um, it started with that. And I picked up stuff on my tape recorder that I could not explain. And I was thinking that because that's not an ultrasonic field, that's an electromagnetic field, I was thinking maybe I could do something along that line. Um, but the really big problem with that is the interference of all the radio stations and all this other garbage that exists in our three-dimensional atmosphere, um, with the magnetic fields and the resonant circuits. They all pick that stuff up. But if you use light waves like a laser or black light, which is the ultra it's the black light frequency. Ultraviolet, that's what I was thinking, not ultrasonic. Ultrasonic is 500 kilohertz. Um, and that's actually another realm of study, but I don't go into that because I just, I don't know about that field. I'm trying to get into the light waves, because if you use light waves, you can almost guarantee there's nothing that's going to be interfering with that input signal. Yeah. So anyway, I think what I got to do is, so if we look at we're going to look at the specs on this. This is a 3904, and that's a 3906. So collector emitter voltage 40, emitter base is 40, 60, emitter base 65 volts, collector current 200 milliamps, 200 milliamps, same temperature range, wattage. This one is 625 milliwatts. I don't. That's a lot of power, because we're talking tens of milliwatts here. This one. Yeah. So the 222. Let me see if I can find a PDF on this one. What equation determines this field of strange attractors are nonlinear chaotic phenomena in some equations on the system? So we can't be talking about Maxwell. Well, the that's kind of a loaded question. So the Maxwell equations define your electromagnetic field, and um, it depends on how the field is generated, whether it's linear or nonlinear, maybe. Um, yeah, there's definitely no linearity when it comes to these other fields, because what you're doing is you're peering into infinity, and so that's theoretically that's a nonlinear progression. But if you bypass the approach to infinity and you go through a wormhole, there's no there's no linearity, there's no nonlinearity. It's just some field that's been created so that you can do this FTL communication, because you don't know where this other communication is coming from. It's going through space and time. It's going through some other dimension, some other universe. Uh, it could be, it could be a gazillion light years away. And how is that possible? Because, and then what's really weird is that they use a lot of the strange attractors and fractals in biology, microbiology. They use it in chemistry, and they even use it, I think, in some communication systems. They're using it for uh, secure. Some of it they're using it for secure encrypted communication systems, but it's not typical type of thing. I don't know exactly what says what equation determines this field. Well, you want to think in terms of math. It's a strange attractor. Um, well, maybe and maybe not. Okay, it's so lasers are created by bouncing light back and forth between two mirrors, and then you get an output. It's a very strong output. So there's two things. You could have a resonance. You could have a resonance between these two mirrors, and you can do that by adjusting one of the mirrors very very close, so that it becomes a wavelength. It's not there could be like 100 wavelengths between the two mirrors, not 100.1 or whatever. So you set it to an exact multiple of the wavelength, and you get a resonant cavity. And that's actually another part of this, is because if you can create a resonant cavity, that also gives you a lot more amplification. Um, but maybe I don't want a resonant cavity. Maybe I want the laser information to disappear. I don't exactly know, but those adjustments with that micrometer, when you're changing the mirror, they're so small. It's like one micrometer is 1,000 nanometers, and the wavelength of the ultraviolet is in the nanometer range. We're talking like tens of nanometers. So I thought, how am I going to do that? So I'm going to use gear reduction ratio, and I'm going to use the micrometer to control a longitudinal axis to get gear reduction, and that's a whole another ball of wax. Like, how am I gonna do that? It's possible, I think, and that's actually going to be a tuning. It's like a tuning thing. It's sort of like tuning a waveguide or whatever, but um, and that it's going to do something. So I'm going to create the feedback field, no matter where it is. I'm going to be able to adjust that feedback field to eliminate noise and look for a signal in that feedback field. That's the whole. That's the whole idea. I don't understand the math of the feedback field, but I know how to create it. Let's put it that way. Um, for lasers, you got two mirrors. You bounce the light back and forth. And if I understand chaos theory, I can also do this with an electric circuit. I can create a feedback field, and it's like with a guitar. If you put the microphone too close to the amp, you get this screeching sound. That's a feedback. So, and if you put it too close and you just leave it there, it's going to go whip right off the roof. But if you adjust that speaker and that microphone just at the right spot, you can get you can create an audio feedback field, and it won't go through the roof. It will just kind of sit there, and it'll kind of make some noises. And so it's that noise energy from that almost hitting that feedback field that creates a strange attractor. There's strange attractors that occur in that, and then that's where you get that's where you could get information. But that's just audio. That's just using audio, and I don't believe by creating an audio feedback field, I'm going to peer into the next dimension. It's not going to happen, but it's possible. You know, wherever there's a feedback field exists, there's something going on in there that we can extract information, and it just seems. I think this is part of the FTL. It's part of the alien technology. It's part of all that reverse engineering stuff that we supposedly got into back in the day and never told anybody about it. Anyway, enough on feedback fields. So this one here, this is 2N222, 600 milliwatts. This has total device dissipation. I don't care about that. 625. I mean, it's close, but let's see now. We gotta get more specific here. What am I looking for? Maybe input resistance. DC current gains. I'm specifically interested in the input resistance or the input impedance and output impedance at certain frequencies. So this has a range of 300 megahertz. Output capacitance 8 picofarads at 1 megahertz, and this is all audio, by the way. It's also like we could have a signal that's a pulse wave. It could be frequency modulated. It could be pulse width modulated. It could be amplitude modulated. It could be anything. So we want to look at this stuff here. Let's see if we can go back and get some information here. This is the AMPN, I think. It should be. 100 milliamp as a switch and to 100 megahertz as an amplifier. This one, well, it doesn't really say. It's also 100 megahertz. Collector current gain minimum, maximum, collector emitter voltage of 1 volt, HFE. Okay, let's look at this one. DC current gain HFE at your different levels of milliamps. Collector current, and these are the gains. Oh, they've tested this at minus 55 degrees. 35, 50, 75. This is 40, 70, 100. This looks like the 3904's got more gain. Base emitter saturation 0.65 volts. That's a diode voltage. Small signal characteristics. Delay time, rise time. This has to do with transients. That's in the nanoseconds. 35, 200. Oh, this is 8 picofarads. It's the same. Input impedance. I didn't see that on the other chart. The 2222 has a this is 30 volts, 15 milliamps. It's 25 nanoseconds. 225, 200. I mean, it's close. So now my question would be, what exactly is 25 nanoseconds? Let's see. Let's go over here. And what we do is we divide 1 divided by point. That's 1 microsecond. This micro is 6 nano. 0. That's micro. I believe that's 25 nanoseconds equals. That's 40 kilohertz. Let's see. 1 divided by point 123.050 is 20 kilohertz. So that number, if that number is lower, that gets us a higher frequency. So that's within the audio range. Anyway, I don't know if that's I don't know what this is. Rise time? It has to do with I mean, I can do pulse width test circuits. My other question is about the resistance here. This has an input impedance 1 milliamp at 1 kilohertz is between 2 and 8 k ohm. That's that one. What about this one here? Doesn't really say. It must be in the k ohms. I'm thinking I'm going to use this 3904. That's what I'm thinking. Or I could try them both, you know. Just put we put our calibration circuit in there, our calibration signal. Voltage feedback ratio. I don't know what. Okay, input impedance. So if the collector current goes up, the input impedance in k ohms is going down. At 1k, this is 2, 2, 3, 4, 5, 5 milliamps. That doesn't. I don't really understand this. Delay and rise time equivalent test circuit. Oh. Okay, I could probably use that. I could set this up and look at. So that's not too bad. That's 300 nanoseconds. A 2% duty cycle. .500 microseconds. Yeah, this is just something I would have to test frequency response of the amplifier. I don't think it's a problem. But this dude, I don't know. Oh, they've got, so this one is, this one is, this one is going into the negative. Yeah, huh. See, my problem is I've got to look for a, I got to look for 2N3906 Class A audio amp, which is kind of weird. You just don't use a PNP transistor for amplifiers. Maybe it's more for switching, I don't know. Modified input circuit for high input impedance. Okay. Basic Class A circuits. Oh, that's NPN. I don't want that. Power amplifier circuit. I don't have the power amps hooked up yet. Well, where's that one? Modified input circuit for high input impedance. So there's your FET, and that thing's pointing in the wrong direction. That arrow is pointing the opposite direction here. MPF 103. MPF 103 versus MPF 102. Substitute. I got a bunch of these too, but these are like high frequency. I don't know, remember if I use these. I honestly don't remember. I'd have to just build a circuit and do some tests. Because all I'm doing is just basic audio amps, that kind of thing. Let me see here. What is this? Image. Yeah, see, they got the arrow pointing in. That's what I thought. So that picture is not correct. Here they're showing the arrow pointing out. Maybe that's just the signal going out. Are we looking at web page here? We are. Okay. So there's that circuit. I could probably, this is 22K modified input circuit for high input impedance, 1.5 megohms, 580. The output impedance of the preamp is more than a few thousand ohms, a few K. Okay, that's good. The input stage of the amp modified to include an FET source follower, as shown in figure 8. This increases the harmonic distortion and is therefore theoretically a less attractive solution than a better preamplifier. 10.12%. Well, let's see. Yeah, I'm looking at this. What about the input impedance? Small, adequate sink area, etc. Fleet which must be paid for. It says supply voltages and above currents involved lead to dissipation. 17 watts. I don't care about that. Adequate heat sink must be provided. This, unfortunately, is a penalty for Class A amps. I'm using a Class A amp for very low power. Adjust so that VE is, what is that? 1/2 V, I think. Oh, and they're using a 3906 on the output. I wonder if I can put, why would they put a 3906 Why would they put a 3906 there? Let's see. Can I save this image as documents? My projects. This is FET1. It's very simple. I mean, this seems like this is what I'm looking for. 22K for stereo. 22K. 39K, 1/4 watt. Huh. Somewhere I don't know why I got my headset on, because I don't really need that on. I thought that I had a book that had FET circuits in it, but God, me to try to find something. I think there's some in them other little books. Maybe I'll build this. Or something similar to this effect. This has got to be... My question is, I need to build something that's similar in both cases. And it's just interesting that they're showing this 3906 sitting here. This is just too coincidental. This is so coincidental, it's not funny. I think I can start building that circuit. So this is just this basic stuff, is what it is. Now, what I'm going to do is I'm going to go ahead and take this back off. And we get all this mess happening here. I need the circuit to be up here. I need that to be over there. Now, my microphone's going to be a little bit not so good now. As you can see, I've got stuff here from ages ago. These are op amps. There's a 3906 here. And I need to find a 3904, which God knows where that is. I got tons of stuff. I got cables everywhere. We were doing an op amp setup, and I'm not happy with it. In fact, I'm so unhappy with it that I'm probably just going to dismantle everything here, because it just really was not conducive to my lifestyle. Now, a lot of these cables and stuff that I got going on here has to do with looking at the phase of the inputs and trying to determine that there's a 180-degree phase reversal from... Is this stuff plugged in? Oh boy. Nothing's plugged in here. We gotta plug in our stuff and make some smoke. Let's see, which one is that? Ain't that one. Not that one. I got so many fucking plugs here, it's crazy. Because I don't know what's what, you know. That one. Okay, that should be... That's my frequency counter. And I should label my plugs. That would be a good thing to do. But I'm too lazy. What do we got here? Nope. No. voltage meter thing. I don't even need that actually. I don't want that one. What's this white one? No idea what this white one is. I don't think it's that one. Not that one. Oh, we got our scope. And I want, there's this generator. I want these generators up. Get them warm. I got my trusty, dusty power supplies. All this crap's gonna get disconnected because it's just not what I'm doing. Oh, you know what? I had those resistors in there for a reason. But they're not there now. Just gotta get this. These cables need to be moved. All I'm doing is just building a basic amplifier circuit. However, my problem is I want to see 180-degree phase reversal in a circuit somewhere, and I want to have it produced such that it's produced with the least number of components possible. That's the whole idea. That's why they're called discrete circuits, that kind of thing. What do we got here? This needs to be somewhere. With a rainbow. I don't know what's in that box. Yeah, I got too much stuff. I got cables. I gotta test all these cables. At some point in life. That's a bell. Let's put this up here. I use this bell to test harmonic sounds whenever I get to that point in life. I got some laser pointers here. That's much later in the game. I don't want to put that there. Shit, I put these right here. This is my static electricity antenna. Let's not put that in there. I could have hundreds and hundreds of gazillion voltages on it. I got tons of little speakers. Once we get the little speaker amp built, all these tools need to be gotten out of the way. I gotten better. Like, I got to a point where when I started doing stuff, I couldn't see my desk. It was not good. Not good. I don't need that humongous thing sitting there. Got some garbage floating around. This typically goes into my attenuator. Some stuff there. I don't need that circuit. We're going to pull this amp. Actually, what is that? I got to use a magnifying glass to see anything. That's a 741. I need to build a 741 test circuit. Get rid of all this shit here so I can see what the hell is going on. So yeah, I have yet to build a circuit that I can see my 180-degree phase reversal on a signal. I want to see it. And we could use this FET setup that we need. Let me think here. I got two of these. I want to power this one up and this one. I gotta figure out which is which. there's that one. And I'm going to power that one up. That's not the plug for that one. It's this one here. Well, la-di-da. What the heck is that plug for? What the hell is the plug for? There we go. Alright, I got 2 oscillators warming up. I made some money. I gotta find out what time it is. I'm all ready to build this circuit, and now I probably gotta take a break. Let's see here. What is this mess? Why isn't there a wire on this? This is supposed to be the input. This is the external trigger. That's channel 2. That's the external trigger. And the input is connected to that other cable. Listen to this fucking squeaky chair. Oh God. What time is it? I gotta look at my... I gotta get my phone and check something here. Yeah, so like... I'm sort of waiting for a phone call. Well, I found a 3906 and I got a bunch of transistors in here. And I'm wondering, like, see? All kinds of shit. And I'm wondering... I don't think these are what I'm looking for. I don't know what these are because they've got gold leads on them. Yeah, I have no idea what those are. Motorola 417s. Yeah, I think I gotta go. What's this here? That's a 39. I don't know what that is. Now, what is this? Because this one's got red and that one's got green. I don't think what I'm looking for is in there. What I need is probably in my yellow box, which is down here. What's going to be interestingly fun is getting into the transducer circuits. That's where the action is. Now I gotta get my magnifying glass here. See if I can find... I need to find an FET and I need to find those other ones. I don't think there's transistors in here. I think they're in the little boxes. I had an accident with a box, and everything got strewn all over the place. They might be in that other box, which I put someplace. I've got this. Those are just ICs. Oh shit! What is in here? I gotta be careful because I got tests happening with some of this stuff. Oh, we've got some transistors here. We've got some transistors. Okay, fuck out of my face. Seriously? There's a 2N4400. That's a bit of that's more of a high signal amplifier. And we are in luck. We have a 3904. Let's see what else we got here. This looks like a 2N. I think that's a 2N222. That's got an A on it. There's some op amps in here. I wonder if these are my LT1024s, and they're all upside down. I don't know what that is. We got some components in here. There's a variable capacitor. We got some capacitors. We got color-coded transistors. What the fuck is this? Two N4402. I don't know what that is. Shit. Oh, I got one transistor in there. You believe that? I came up with one transistor. That's crazy. Well, actually, I got the 2N222. Yes. I know I got more of them. Those are ICs. Those are ICs. All ICs. And 3906. Oh, wait, I don't have the 30. That's okay, we don't have to have that one right now. I'm just gonna build the amplifiers for the output stage. I gotta see what the pins are. It's a 3904. 3906. Well, I don't know. Let's see. 3904 spec. 3904. 1, 2, 3. Emitter base collector. Emitter base collector. So the base is always in the middle. The emitter is on the left, so we're going to put this in. The emitter should be on the right, because that's our output. Okay. Actually, let's put this over here. Oh, what the hell? Fuck you. Goddamn little Where's that circuit? They've got a 4.7K to ground. Let's see. Wait a minute here. 3904. They probably don't have a circuit in here, do they? 10K. 275 ohms. 275 ohms with 3 volts. We know that the collector emitter voltage is in the 30s. We'll just double verify this. Collector emitter is like 40 volts. Collector to base is 60. So let's grab a 4.7 and a 10K. In this stuff here. Gotta use my trusty, dusty magnifying glass. I think there's a 10K in there somewhere. Let's see what we got. There's one there. I could use that one, I guess. I believe that's 10K. I have several meters to test my voltages and resistances and all that good stuff. Well, that's not going to work out very well. This is 9.93. That's close enough for me. That's going to be, so it's collector base, so that's going to be from the base to right here. It's collector base emitter. Wait, no. NPN. Am I doing that right? Collector base emitter. So the collector's got 300 ohms. 375 ohms. 200 ohms. 400. Why is it using 375 ohms? I don't know what this resistance is here. Well, let's find out what this resistor is. Da 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 da. Scooby Dooby Doo. I don't know what I'm doing, but what am I gonna do? Oh, look now, boy. Wait, no, we test to find out what that variable resistor is. We test the leads on the end, and that gives us the total resistance of the variable resistor. That's 50K. Holy glockenspiel. I don't want that. What do we got over here? Can you read this stupid thing? That's a 50K. This is, I don't know what this is. It's green to orange white. White orange. Shit. My eyesight's seriously, come on, that's 100K or something. It would be nice to put a variable resistor in there. This is, what is this thing here? That's a 2K resistor, ain't it? Yep. I got a lot of stuff. I don't know why that's freaking open. What the hell is going on with this thing? I don't seem to have a resistance here. Yeah, something's wrong with this resistor. Shit. Well, maybe I don't need to be too specific with that. That's a current limiting resistor. That's 100 ohm. Wait, that's a 10 ohm. What's this one? You gotta get the right stuff. What the hell? 2,000 ohms. That's 100 ohms. I'm supposed to have 375 in there. That's a 10 ohm resistor. Good lord, that's a small one. I could take two 1Ks and put them in parallel. There's another 100. You know, I think that's what I'll do. Oh, what's this one? This is 220, 320. I want to put two 1Ks in parallel. That's what I'm gonna do. That'll give me 500 ohms. That's a 1K. That's 1K. Alright. We put these in parallel. We get 100 ohms. That's to the collector. And that would be a message. I don't know why they're coming in all at once now. Uh-oh, I may have to call it quits. I'll be back and I will continue this circuit tonight. We are making progress. Never fear. Thanks for watching. I should be back. I don't know what time is it. 6, maybe an hour. I might make something to eat, and we will continue this endeavor.